dear students. Today we have proposition 35 in book 3. If in a circle two lines cut one another, the rectangle contained by the cut lines of the one is equal to the rectangle contained by the cut lines of the other. Okay? First, we'll do this in a real simple way. I forgot to do this one. If it's a square, if they cut each other at the center, that's easy. The rectangle contained by this and this is equal to the rectangle contained by that and that, because this and this and this and this are all equal because they're radii of the same circle. So here we have a circle, two lines cutting one another at the center. Therefore, the rectangles they make, the rectangle of this two cutting lines will be equal to the rectangle of these two cutting lines because they'll be squares and be equal. All squares are equal. All squares have, the sides are equal. That's it. Okay, now we have the complicated case. It's a bit of a complicated proposition. You might have to watch this twice. Here we have a circle, two lines cutting each other, not at the center. Thus, it is required to show that this rectangle, the rectangle contained by this and this, is equal to the rectangle contained by this and this. Okay? Let's take the center of the circle. We know we can do that. Okay, let's drop perpendiculars from the center to the lines. Okay. Perpendiculars. Okay. Now we know that if from the center a line cuts another line, a line is dropped perpendicular to another line, that line dropped perpendicular from the center cuts that line in half, bisects the line, cuts it in half. So this has been bisected here, and this has been bisected here. Okay? Let's connect some lines here. Connect some dots. And from the center to that line of point of contact, and say from here. And here. Okay? Good. Not a very good, pretty line. So, here we have a straight line cut in the middle and cut not in the middle. So a straight line's been cut into equal parts and unequal parts. If you remember from book 2, we know that if a line's cut in equal and unequal parts, the rectangle contained by the equal parts, by the unequal parts, the rectangle contained by the unequal parts, plus the square on the line between the points of section, the two cuts, the equal cut and the unequal cut. So the rectangle contained by the unequal parts plus the square on the line between the points of section will be equal to the square on the half. So we know that's the case. The rectangle contained by this and this plus the square on this is equal to the square on this. Let's add, see this blue line that was dropped from the center to cutting in half? Let's add the square on that blue line to both sides, just for fun. It's a little trick we're going to do. So the square on this is added to both sides. So now we know that equals added to equals, the wholes are equal. The rectangle contained by this and this plus the square on this plus the square on this is equal to the rectangle, the square on this plus the square on this. Great. But look at this here, it's a right angle. Remember we dropped this at right angles. So this is a right angle triangle, and this also is a right angle triangle. Therefore, the square on the hypotenuse is equal to the squares on the sides. The square on this hypotenuse is equal to the square on this and this. The square on this hypotenuse is equal to the square on this and this. Okay? So because, I'm going to repeat what we already know, and then we'll see that because these two squares are part of one side of the equation, and these two squares are part of the other side of the equation, that we can just replace them with the square on this and the square on this. So watch. We come to the conclusion already past that the rectangle contained by this and this plus the square on this plus the square on this is equal to the square on this plus the square on this. But the square on this and the square on this is equal to the square on this, because this is the hypotenuse of this right angle triangle. And the square on this and the square on this is equal to the square on this, because this is the hypotenuse of this right angle triangle. Therefore, we can say that the rectangle contained by this and this plus the square on this is equal to the square on this. Great. But look at this line here and this line here. It's a terrible drawn line, but they're both radii of the same circle. We connected from the center to the cutting points, okay? So these two green lines are equal. Well, if they're equal, the squares on them are equal. So the square on this is equal to the square on this. But the square on this was proven equal to the rectangle contained by this and this, plus the square on this red line that's dropped at the cutting point from the center. Great. Now look at this line. We can do the same thing over here. We have a straight line cut in half because it's been dropped perpendicularly. Okay? And cut unequally right here. So we know that the rectangle contained by the unequal parts plus the line between these points of section is equal to the square on the half. And we can end up showing then that in the same way we showed it with this line, that the rectangle contained by this and this plus the square on this is equal to the square on this, just like we showed it over here. Okay? So now we have two things equal to the square on this. The rectangle contained by this and this plus the square on this is equal to this, and the rectangle contained by this and this plus the square on this is equal to this square on this as well. Therefore, they're equal to each other. Therefore, the rectangle contained by this and this plus the square on this is equal to the rectangle contained by this and this plus the square on this. Look, we have the square on this on both sides of the equation. Let's take it out. Equal subtracted from equals are equal. Therefore, the rectangle contained by this and this is equal to the rectangle contained by this and this. But look, those were our original lines in the circle, where they cut each other not at the center. This line cutting this line here at the center. And it was required to show that when two straight lines cut each other in a circle, the rectangle contained by the two sides so cut of one line will be equal to the rectangle contained by the two sides so cut of the other line. Quod erat demonstrandum. Thank you. Bye-bye.